Excellent. Okay, so I'm going to be talking about Pachner Moves, and this is a way to decompose homeomorphisms between simplicial complexes. So in case you find this extremely interesting, the guy's name is Udo Pachner, and there's like one major paper on this, so you won't have any real trouble finding the whole rigorous details and everything. So let's just get started. So I want to make sure everyone's on the same page, and we define like a simplicial complex first. To define a simplicial complex, we need to define a simplex. So we need, in Rn, we need n plus 1 affinely independent vectors. So Vn in Rn plus, well, n plus 1 in Rn, right? And affinely independent means that V1 minus V0 up to Vn minus V0 are all linearly, V0, are all linearly independent. So you have these n plus 1 vertices, basically, and if you look at the edges, which are these differences, starting at any vertex, you'll see that they're like linearly independent. So in 3 dimensions, we can make a tetrahedron out of these, and in 2 dimensions, we make a triangle, etc. So to look at the actual definition of what a tetrahedron and triangle is, we just look at different linear combinations of these vertices. So an n simplex is a set A n Vn plus A0 V0 such that the sum of all AI equals 1. So the motivation for this definition is basically we want any point, we want the thing to be the smallest convex set which contains these vertices. So if we had all AI equal to 0 except for 1, say an, then that point would correspond to the vertex Vn. And if we had only one vertex, only the coefficient for one vertex being 0, we would be on the face opposite to that vertex. So just to draw some pictures, if we were in 1 dimension, our one simplex is just a line segment. In 2 dimensions, or 2 simplex, is a filled-in triangle. And in 3 dimensions, we have a tetrahedron. That. I'll draw bigger, better pictures soon. Does anyone have questions about what a simplex is? No? Okay, excellent. So a simplicial complex is just you take some number of these simplices and you glue them together so that the intersection of any of the simplices is also simplex. So for example, let's just take 2 triangles and a line segment over here. This is a simplicial complex because these 2 things are simplices. This is a simplex, and if you intersect any of them, you also get a simplex. An example of something that is not a simplicial complex is if you had like 2 triangles and you had another triangle, but you glue it so that there's this overlap, which is not a simplex. I mean, in this drawing, it looks like it could be a simplex, but it's not. If you like smash one triangle into the other so that it actually goes into it, that's no good. So let's talk about homeomorphisms between simplicial complexes. Where's my eraser? Yeah, here we go. So do people here know what a homeomorphism is?
Roughly, but can you go over it?
Yeah, sure. So we have a homeomorphism. It's basically a function from one simplicial complex to another, which is continuous and has a continuous inverse. So an example would be, say we have a simplicial complex which looks like this. And triangulated like that. Lots of triangles. Something with a lot of triangles like this could be continuously deformed into something somewhat simpler, such as, let's do it like this. Right, so we can, the simplices don't have to be preserved, right? It's just the fact that we can go continuously one way. Oh, sorry, I should specify that this is all filled in, right? So I'm thinking of an annulus, right? So this guy is filled in. They're both homeomorphic to an annulus, or equivalently a cylinder, right? So the key is that you can continuously deform one way, continuously deform back. So there's this way to represent simplicial complexes combinatorially using just a set of sets. So if you have this really simple complex that I mentioned before, it's just two triangles and a line segment. And we label the vertices, let's say A, B, C, D, and E. Then we can represent each simplex as the set of its vertices as well as the set of each of its edges. So if we were to look at this simplicial complex as a set, we could have the set C, B, representing this triangle. We would have, this is going to have a few elements, but C, D, E, representing this triangle, right? And then every edge and every individual vertex. I'm not going to write them all out because that would be really tedious. But this is a combinatorial way of representing a simplicial complex. And the key observation is, well, not the key observation, but a good observation is that if you have any simplicial complex which have equivalent combinatorial representations, meaning you can just relabel the vertices and you get the same set, then they're homeomorphic. All it corresponds to is skewing and scaling the different simplices in the complex. But the question is, if we have two combinatorially distinct simplicial complexes like these two guys, as you can see, if we were to actually write the combinatorial definition of each of these, they would be very different. How can we get from one to the other? How can we explicitly construct a map from one to the other? And that's basically the motivation for Pachner Moves. So the one-dimensional case is very easy. Should be able to see the one-dimensional case immediately. Say you have just a line segment, right, and some simplicial complex which looks super weird, but is like homeomorphic to a line segment. What are the atomic combinatorial moves that you can do in the line segment to get to this?
Bisect it.
Yeah, exactly. So this just goes to two line segments, and then you can bisect each of these iteratively until you get this. And that's exhaustive for any one-dimensional complex, and you can also do the closed case equivalently. So in two dimensions, there are two cases. There's two cases in every higher dimension. So one is we have a triangle, a solid filled-in triangle, and we take the barycenter. The barycenter is, if we look at these coefficients, right, we set each of them to 1 over n plus 1. And then the sum is 1, and it falls exactly in the center of the triangle, right, because it's just the average. Okay, so we take the barycenter. We draw simplices to each of the boundary points, and then we've subdivided it into 3 triangles. That's one of the 2 cases for 2 dimensions. And I'll go through examples of actually showing how different simplicial complexes are homeomorphic, like after I get done defining this. Then the other case, which is perhaps even simpler, is if we have 2 triangles glued together like this, then we take that to, this is going to look really trivial in 2D, but it's quite useful. It's just the same structure, except it's cut down this diagonal instead of this diagonal. And the reason that it's significant is because this structure of 2 triangles can occur in a larger simplicial complex where you have more structure this way and that way, but you can always switch the direction of the diagonal. So somewhat local move. So that's the 2-dimensional case, and now I'll describe the general dimensional case. So if you have in n simplex, I'll draw the 3D version like this. If you have an n simplex, so a 3 simplex for example, then you take the barycenter, you draw you draw your edges to each of the vertices. Is everyone still clear on what's going on? This point is the barycenter. These are each of the vertices. I draw my new edges, and then I thicken. Well, I draw sort of faces here, and I form 4 new tetrahedra in this case. So yes.
We have colored chalk if you want to use that to like.
Hey, that'd be useful.
It's on the
Mine.
Wait, so are you sort of like constructing the dual to this thing?
No.
So how are you getting these 4 tetrahedron?
Well, you take the barycenter, right? And then you sort of conify each face to the barycenter. Because the tetrahedron has 4 faces, so each face becomes a new tetrahedron.
Wait, and you what the faces?
Like conify them, like turn them into a cone. Like you extrude them to a point.
Oh.
Why does it have to be the barycenter? Why can't it just be at any point in the interior?
It can be. It's just easy to talk about the barycenter, like
Okay.
geometrically. But combinatorially is all equivalent. Yeah, I'll draw those subdivisions using color chalk. Okay, so I'm gonna draw a barycenter here. Okay, so these are the edges of the new simplices, and you're going to get 4 new tetrahedra out of performing this move on the single tetrahedron. And in general dimensions, you can get n new simplices out of a single n simplex. Can you guys see how that works?
Wait, how's this the generalization of that one?
This is the generalization of this one.
Oh, okay.
Yeah,
I see.
yeah.
Yeah.
Cool. Yes.
n simplex referring to the dimension or the number of vertices?
The dimension. So an n simplex is a simplex that is n-dimensional, and an n simplex has n plus 1 vertices.
Okay.
Combinatorially, the edges of an n simplex are just a complete graph on n plus 1 vertices, which is somewhat important. Okay, so the higher dimensional generalization of this is just take the n faces, n plus 1 faces of the n simplex and extrude them to the center of your n simplex. For this one, we're going to have two n simplices on top of each other. I should draw it the way. So this is going to be on top, and then one on the bottom.
So they share a face?
Yes, they share a face. Yeah, they share one face, and there's always two vertices which don't intersect the other simplex. So obviously all three of these vertices intersect the simplex, and when two n simplices share a face, they share n of their vertices, because there's n vertices to a face, right? So to divide this, we look at the two vertices which weren't intersecting, like we did here, right? These two didn't intersect when we had it moved like this. So we're going to look at these two guys, and we're going to draw straight down the middle, and then each new simplex will come from basically drawing a face from this edge, these two edges, and then from this edge, these two edges. I should draw a bigger picture just so everyone can see. Alright, here is one of our tetrahedra. And here is our second tetrahedron. Does everyone see the two tetrahedra? Is my drawing clear enough? I can dot this just to make it clear which one is behind. So say that this line segment intersects the face which they share here, then our new edges will be drawn like this. So it's kind of like this move in one lower dimension, except what we're doing is subdividing these n simplices. And we take these two n simplices and we get n simplices out of them. Does everyone see how this works in 3 dimensions? Can everyone imagine how it works in n dimensions where you have two n simplices sharing an n minus 1 dimensional face?
I mean, visually this is difficult.
Does everyone see why if we glue simplices at a face, there are always two vertices that don't intersect? Right? Because if we're gluing them on the face, there's only one vertex which isn't in that face for each of them. So we have our two simplices like this. We have vertices here which don't intersect the other simplex. We can draw a line segment that goes from one vertex to the other that passes through the shared face, and then each new set of n-1 vertices gets a simplex made out of it in this sort of cutting fashion. It'd be nice to have like sculptures to like take apart. Yes.
So if you have two n simplices, your claim is that you get this subdivision yields 2 times n.
Just n.
N.
Mhm.
So in this picture, you have three simplices, and you get out 6 from this.
No, you get 3. Sorry. I should make it clear that this disappears.
Oh,
Right.
it's not a face anymore.
Yeah, this is not a face anymore.
Oh.
Okay.
Yeah, sorry.
Mhm.
So if we go back here, right, this face disappeared, right? We're just left with the line segment that crossed through it from the 2 vertices that weren't shared. Yeah.
So are you assuming that none of the angles are obtuse? Because you're saying that there is a line between those 2 vertices that goes through the face. But like in this example that you've drawn, if I just take the 2 vertices and I stretch them both very far to the right, then the line between them just won't go through the face.
That's true, but then what you're saying is combinatorial equivalent to this.
Right, but so you're considering like regular shapes.
Because the simplex is defined geometric properties.
Right, but however we change the position of the vertices, that always corresponds to homeomorphism of the symbolic complex. And in some sense, it's a trivial homeomorphism, right? Because we don't actually change the combinatorial structure of the symbol.
Yeah, I get that. I'm just saying, like in that case, the line wouldn't go through the face.
Yeah, in the geometrical sense, yeah. But basically, you can fix that geometrically if you wanted to by just picking the barycenter of this face, drawing the segment that goes from the top of here into there, and subdividing like that, and then going down. Is everyone on the same page with how these moves work? Yes.
In the picture that you drew, are we considering the cavities?
The cavities?
Yes. Because,
These are solid.
yeah. Because before you have 2 tetrahedron, solid tetrahedron, and then after the subdivision, you have what seems to be
3.
more sides.
3. Sorry. I'll try to draw the result.
Okay.
Let's see. So
Sorry.
how? No, it's fine. It's just it's difficult to. I mean, you can kind of see the results in here. So take these 4 vertices, right? Well, yeah. Then the segment that goes through here is the edge between these vertices. So there's a segment here that connects these vertices, and likewise for these 2, right? So we have a tetrahedron there.
But don't you have, so you have like this middle bar, and then it goes in for a triangle, and then you have the 2 peaks? Like,
2 peaks. Well, remember that this like whole thing right here is 1 simplex. This whole thing right back here is 1, and then back here is 1 as well. Yes.
I don't see how it's a simplex because it has 5 vertices before.
Well, we this intersection point, like it's kind of like fake, right? It doesn't count as like a real vertex once you actually perform the subdivision.
okay.
Yeah. The higher dimensional version might be a little bit difficult to visualize. Huh?
He's serious.
I mean, like algebraically, you can sort of just think about like the properties of like these objects, right? And how like to one face there will always be n vertices, And so there always, when you have two simplices glued to the face, there will always be two vertices which don't intersect. And then you can sort of pass it through and define new n simplices based on cutting along the line that you intersect, that passes through these to each set of vertices that you already have. Sorry, this is a little difficult to describe. It's just literal hand waving. So I want to do an example in a 2D, right? Everyone gets the 2D version, right? The 2D is pretty straightforward.
But maybe I missed something, like, so what are we trying to say about these moves? Like, I understand, what are we actually
Oh.
saying?
So, it's like been proven that if you have a closed n-dimensional simplicial complex, then any homeomorphism between them factors into these moves.
Okay.
If your simplicial complex is not compact, then the sequence of moves that relates them might be infinite. So, in that case, you might not have like a nice relation. But if we have time, I'll try to show you how to deal with simplicial complexes with boundary. But for now, we're just dealing with compact without boundary simplicial complexes.
And when you say like closed and compact, that's under the topology induced by embedding it in Euclidean space.
Well, I mean, you get a manifold topology just by having these simplices glued together, right? Because each individual simplex is this, so you get a homeomorphism to an open set in Euclidean space. And then when you have the gluings, same thing applies to the faces, right? Yeah, so I guess you could kind of think of it as embedding it in Euclidean space, but yeah, whatever fits your boat.
In general, you can think about the geometric realization of an abstract complexes looking basically at infinity. It gives you enough space to do these all together without running into things, and you don't have to consider stuff about like taking simplices from different topologies and trying to link them together.
So there's these moves allow us to find a homeomorphism between any two polyhedra, right? Because polyhedra have a topology of a two-sphere. So let's just take some polyhedra and figure out how they're related. So let's take a tetrahedron, the surface of a tetrahedron, right? And I want to, what's the name of octa something? Octahedron, yeah, that's what I'm about to draw. Okay. Does everyone see how the octahedron is? It's just two square pyramids stacked on top of each other. Cool. So, some things to note about these two polyhedra. Here, every vertex has 4 edges coming out of it. And that's the name of the equation, really. And we have 6 vertices. So, let's just start messing around. I mean, we need, how many do we need? We need 8, yeah, we need 8 faces, and here we only have 4. So, how are we going to get more faces for this guy?
You triangle cutting one.
Well, which one's that?
You like take the very center and
Yeah, you got it.
Yeah.
Okay. So I'm going to draw this like this. So this is just a tetrahedron, right? This is a square, triangular pyramid. And then I'm going to take these two faces, and I'm going to divide them like Spencer said. Does everyone see what I did there? Excellent. Okay. So now we have how many faces? We have too many faces?
No.
Each one, two,
You have enough.
have enough faces. Thanks for coming. Okay. So now the only thing that's missing is the fact that there's 4 edges coming out of each vertex. So how can we change that? You guys see how we change that?
What would you have done if there were one too many? Is there like a way to rectify that?
Yeah, each move goes both ways. See, if you had say this sort of structure with triangles, you can always go backwards and just make that a single triangle.
Yeah, but you can only remove
Multiples
Like-
of 3.
n-1 many for like an n-simplex, right? By using that move. So if they differ by something that's not a multiple of n-1, are they not?
Interesting question. Let's see. I'm not sure. I'm going to finish this example before I get too into that.
Okay.
Okay, so we have enough faces here, right? And all we need to do is make sure that each vertex has 4 edges coming out of it. So let's see, this has, how many is this one? This has 4, this has 4, this has too many, this has 6, this has 3. I see what we need to do, yeah, okay. This has 5, and this has 3, yeah, okay. So, we might need to do 2 more moves. Well, let's do, did I miscount?
That's 5.
That's 5. Don't worry guys, I know how to count. Okay, yeah, so there's only one more move that we need to do. Who sees what it is?
So take this kind of square letter between, and then switch it.
Yeah, exactly. So, I'm gonna redraw this. And then what he's saying is we take this edge and we flip it so that it goes like this. And we're done. You can hopefully see that this simplicial complex is combinatorial equivalent to this one. We just take this vertex, we stretch it out, take this one, pull it down, and we got it. You can also verify just by counting vertices and edges and faces if you wanted to. And mind you, there's a face that's behind all this because we originally were thinking of this as a triangular pyramid. Does everyone see that?
So you're looking at it front on, and there's the one that's in the front.
There's one that's in the back, right? Because this is like a triangular pyramid that's coming out of the board, and then we switch that, and now if we just took this, sort of stretched it out, and then stretched this one back, we'd have like the top and bottom vertices of that.
It's like a weird perspective then.
Huh?
It's like a perspective kind of image that you have there.
Well, it's orthographic,
No, I mean like in the artistic sense, not.
Oh, it's artistically, it's the terrible kind of image. Yeah, so there's a 2D example for you. Yes,
Could your spaces have boundary?
they could have boundary. You wouldn't be able to use. I'll get to that next. Actually, let's just do that. So when your spaces have a boundary, you basically have to take the moves that you defined in lower dimensions and use them inductively. So, say you have like a triangle on your boundary, and this edge is the edge that's part of your boundary, right? You have a two-dimensional piecewise linear manifold, and this segment is on your boundary. Then remember, we just bisected the line segment in one dimension, so we just bisect this and draw a vertex up. And there we go. That's how you do it in 2 dimensions. And for 3 dimensions, well, there's also the case where, or no, 2 dimensions is just that, right? So then in 3 dimensions, if we have a tetrahedron, like this, and this face is our boundary, then what we want to do is perform the move which subdivides this face, just like we did in 2D, and then draw a line segment up to the top vertex. And this gives us 3 different tetrahedron, right? And then each of the 3 has a boundary face. So that, and this is kind of like half of that one move in 3D where you had, like if you stacked this on top of another simplex and then did this to both, then you'd sort of get that 3D move which corresponded to turning 2 3 simplices into 3 simplices. Anyway, then of course you would also have the case where so we have 2 tetrahedra which are glued together, and then we form, and this is the boundary, these 2 are boundary faces, and the boundary of the manifold, and what we do is we just perform the move which switches the diagonal, and then we have 2 new tetrahedra. So that's what I mean when you just use the moves that you already defined inductively. You just use them on the boundary faces to define new simplexes on the boundary. And that's how you deal with boundary. Cool. I didn't actually prepare any examples for with boundary, but might as well start talking about convex hulls. So does everyone know what a convex hull is? No? Okay. So, I'll define convexity first, because you know why not. So, our set S is in Rn, and we have any x and y in S, then for all, well, yeah, for all t in the unit interval, we have tx plus 1 minus t y is in S. So that looks kind of weird algebraically, but basically, close one. You have your set, and the convexity property states that if you have any 2 points in your set, then every point in the line on the line segment between the 2 points is in the set. An example where that's not the case is something like this, right? If you have a line segment between them, then there are points on the line segment which aren't in the set. So a convex hull of a set of points is just the smallest convex set which contains all the points. And you can sort of see why if you have n plus 1 points in Rn, the convex hull of that is just an simplex, just based on how we defined it. Yes?
Is it compact?
Well, it depends on whether or not the set that you originally defined is finite. If it's finite, then yeah, always. Because it's like the smallest convex set, right? So if you have a set of points in Rn, they're said to be in general position if, well, let's say R3, let's just keep it 3-dimensional. If you have a set of points in R3, they're said to be in general position if there's no more than 3 points which are coplanar, right? Ajman, you look really surprised for a second. Does that definition make sense?
Wait, how many points do you have?
Any number of points, right? A set of finite points, though. So cardinality is finite, but the points are in general position only if the no more than 3 points are in a plane. So if we take the convex hull of that, that means that the faces of the convex hull will be triangles, right? Cool, because because if you had a face which was like a square, that would mean that there were 4 points which were in a plane. So now for the little demo that I prepared. This has to do with Pachner moves and convex hulls.
Someone get the light by the projector. The projector. Yeah.
Amazing.
Oh, no, keep that one off too. It looks better. Yeah.
Alright, so this is a set of points which is in general position. It's technically a regular icosahedron, so it's not a very general set of general points. But it works for our purposes because the convex hull of this set of points is, it all has triangular faces. So keep in mind, not every point in the set that has been taken the convex hull is a vertex. So there's actually one point which is inside the convex hull, which I'm about to change. Look what happens when I move a single point in the hull. Oh. Amazing.
No,
Okay.
yeah.
That's what happens. So what happens when you have a face that point in your set of points that's behind a face in the convex hull, and you move it forward, is just the Pachner move, right?
Ooh, yeah.
Yeah. So that's the first Pachner move that I showed you guys, and then I'm going to put this back, put it away, and then I'm going to sort of adjust the angle so we can see better. And now, next thing I'm going to do could technically be done by moving just a single vertex. So the interesting thing about this is that Pachner moves can be achieved just by moving single vertices in the set. But I'm going to move 4 different vertices at once, just for the sake of demonstration. So do you guys see what happened there? Like we had these two triangles, these two guys which were adjacent to each other, and then I move the vertices a bit, and what happens after we pass the point where they're not where they are all coplanar, we get a Pachner move, and we don't get Pachner. Okay, you guys see that? So the diagonal was flipped. You guys see that? The coloring's a little weird, sorry about that. But yeah, it is now two triangles which are adjacent along the different diagonal. Yeah?
So the slider is moving vertices and you're just redrawing the convex hull at each.
Yeah, yeah. So the conclusion of this part is that if you have a finite set of points and you take the convex hull, you move one of the points in the set and recompute the convex hull, it'll always correspond to a Pachner move. Yes.
What if you move your point and the thing's not in general position anymore?
Oh, well then, there'll always be like a point where it passes general position.
Can you show what happens when
Sure.
right here?
With that.
What is that? What is that?
Oh, then there's four that are coplanar. Is that
Yeah,
what you're saying?
well, it's not precisely coplanar, but yeah, it's basically, so these four vertices are planar. So yeah, it'll always pass a point where there's like a number of coplanar vertices, but once you just get epsilon past that point, you've made like a Pachner move. And that also works in any dimension, which I think is pretty cool. And that basically concludes my talk.
Does anybody have a question?
Yeah, so you said before that like we decompose any homeomorphism between, I guess, a complex and a manifold by Pachner moves. So like in what sense is can you decompose it like infinite number of Pachner moves? Like in what sense do you mean?
Well, if your manifolds are compact, then it can always be finite.
Okay, yeah.
I'm not sure about the existence theorems for non-compact manifolds, but it would make sense that if there is an existence theorem, then you would have cases where you would have to have infinitely many Pachner moves where eventually you somehow converge to the space where you.
I was wondering, like, do you know in what sense you converge? Like,
No,
where we live in, like.
I don't actually know the non-compact case. Anyone else have any questions? Cool. Glad. Oh yeah, May.
So you said that the simplices behave as like complete graphs on n vertices. Is there a graph theoretic interpretation of Pachner moves? Like in terms of like the traditional graph theory moves, like defining minors and things like that?
I'm not completely sure. I mean, you could always just reduce the what's going on with each Pachner move to the graph of edges, and then you would get moves in terms of graphs. I'm not sure if that'd be useful for graph theory though. Yeah, hopefully that answers your question. Anyone else? Cool. All right.
Very cool.
Yay!
Thank you very much.